So in this chapter, we're going to talk about carbohydrates. Basically, it's more of a bioorganic chemistry than just organic chemistry. We're going to talk about the structure, the reactions, the roles, and so on and so forth. So the term carbohydrate essentially refers to the fact that they often can be represented by a universal formula that looks like this. Okay, so you can see that carbo, and you have this H2O, hydrates. Okay, those are only three elements that are found within carbohydrates. They can be called saccharides, like monosaccharides, polysaccharides, disaccharides, but carbohydrate is some kind of an umbrella name that covers everything from glucose to starch. So, simplest carbohydrates produced by photosynthesis. Okay, I'm talking about glucose or fructose. The reaction that you see on the bottom, if you run it from left to right, represents the process of photosynthesis, which occurs in plants, and then animals eat those plants, break down glucose using oxygen, and this process, the breakdown of glucose using oxygen, is called respiration. Am I making sense? In other words, when you eat, I don't know, potatoes, which contain a lot of carbohydrates, these carbohydrates were produced as the result of photosynthesis. You oxidize those carbohydrates to release energy that is stored in them in the process of cellular respiration. So far we good? Okay. So in terms of the types, there are monosaccharides, such as this. If you take a monosaccharide and expose it to certain enzymes or acid, it will have no effect on it. Disaccharides, which essentially consist of two individual building blocks of monosaccharides, if you expose them to acid or specific enzymes, you will break disaccharide down to two monosaccharides. Okay, make sense? And then polysaccharide, same story. You expose it to acid or enzyme in the water environment, and you can generate many monosaccharide molecules. An example would be, listen, a monosaccharide such as glucose is the simplest one. You can expose it to an acid all you want, nothing's going to happen to glucose. An example of disaccharide is sucrose. When you consume sucrose, acid in the stomach and enzymes in the intestines break down sucrose into individual monosaccharides, glucose and fructose. And polysaccharide example would be starch. Acid and enzymes break down starch eventually into individual glucose building blocks. Does that make sense? Okay. Now you can ask, what about three? They're rare. They're not commonly occurring in nature, so we usually don't use the term trisaccharides. So monosaccharides, there are several classifications here. Monosaccharides can have 3 to 7 carbon chains. Okay? That make sense? So, for instance, this monosaccharide, erythrose, is 4. Okay? and this one has 4. But they are different because the one on the left, erythrose, has an aldehyde group at the end. That makes sense. If it has aldehyde group at the end, we call it an aldose. If a monosaccharide has a keto group, we call it a ketose. You can see that all carbons in the monosaccharide molecule are connected to one functional group. Can you see that? I'm going to highlight other functional groups with a different color. So for instance, in erythrose, the terminal carbon has the carbonyl group in the aldehyde, and then you have these OH groups. In erythrulose, the second carbon is connected to oxygen in a keto group, and other carbons have OH groups next to them. So they have a lot of oxygens, as you can see. Okay? Another classification of monosaccharides is by the number of carbon atoms. If there are 3, we call them trios. 4, a tetrose. 5, a pentose. And 6, a hexose. Okay? 7 is rare, and when you characterize a monosaccharide, you want to highlight both whether it is an aldose, i.e. having aldehyde group, or ketose, having a keto group, and how many carbons it has. Okay? So for instance, if you have a monosaccharide with 5 carbons, which contains an aldehyde group, we call it an aldopentose. A monosaccharide with 6 carbons and a ketone group, we call it a ketohexose. Does the logic of naming make sense, everybody? All right, good. Moving on. Okay. Sorry. So, I'm going to highlight functional groups, and first of all, and then I'm going to count the number of carbons and figure out why they're called so. So these first 3 are aldoses, and the last is the ketose. And then what about the number of carbons? So we have 1, 2, and 3. 1, 2, 3, and 4. 1, 2, 3, 4, and 5, and 1, 2, 3, 4, 5. Yes, I started the wrong one. Okay, 1, 2, 3, 4, 5, and 6. Okay, so by combining the name of the group first, and the number of carbons second, you get ketohexose or aldotriose. Naming. Making sense? Let's name them. So which one is on the left? An aldehyde. Okay, so let's talk about functional groups first. In the example A, the functional group is where? At the end or in the middle? At the end. In example B, it is not in the end. Yes, in the middle. So, which functional group do we have in A? Aldo. How many carbons?
6.
Everybody agrees? What about the second one? What the functional group name? How many carbons?
5.
Make sense? Okay. So glucose, actually everything below 100 milligrams per mil is considered to be normal. And you can see here glucose tolerance test. So let's address some stuff. So basically, the illustration here is not correct. Okay, I can explain why, because I have done a bunch of obesity research and glucose tolerance research in mice. So here's the idea. Do you see the hours after the initial administration? So you can give glucose either as the oral bolus. Somebody just drinks the solution. It's easier. You can do it IV. Okay? Oral is just easier and fast and just so much. Huh?
It's super gross.
What do you mean?
So you have to do this for pregnancy, like when you drink it and then get tested like every hour.
Mhm.
It's disgusting.
Well, so traditionally, basically why there is a mistake here. In case of glucose tolerance test, the normal is considered if you go back to the pre-test values at 2 hours. That's considered perfect. If you're still kind of lingering above, it shows some insulin resistance, okay? Some glucose intolerance. This is a severe hyperglycemia. Now, hypoglycemia like this can only, in my opinion, I have not heard of any physiological condition in which a person, upon receiving the bolus of glucose, would develop hypoglycemia. Something should go massively wrong with the pancreas. Okay, but the point is, yes, how you can determine whether a person has diabetes or pre-diabetic condition, not just by measuring the glucose, but also by administering glucose tolerance test. What is the condition? Like when you come to take the test, what is usually asked of you? To not do something before the test. Water's fine. But yeah, you don't consume anything that contains any calories. Because now, there was a study on how long you should fast. 6 hours. 12 or 18 do not add any benefit. Like, it's still the same results. Okay? So, there are two types of diabetes, just FYI. There's type 1, type 2. So, type 1, which we have here, is when pancreas does not produce insulin enough. Okay? It is autoimmune disorder, usually diagnosed fairly early. Sometimes it's called juvenile diabetes. Okay? Type 2 diabetes it's not necessarily weight gain. It is extremely carbohydrate-rich diet. Okay? So what essentially happens, you eat a lot of carbs, you have a lot of glucose in the blood. Does that make sense? Your pancreas churns out a shitload of insulin. Insulin has to bind to the receptors. Eventually, the receptors become resistant because there's so much insulin. Pretty much just like an alcoholic's liver becomes resistant to ethanol, or a person who has an opioid addiction, their receptors become resistant to opioids. This is why they need more and more dose. Make sense? So, and the person with type 2 diabetes ends up in a very precarious situation. Their blood glucose is elevated, their insulin levels are normal or elevated as well, and when they try to use insulin to bring glucose down, they actually promote that resistance, making it more and more resistant. And the only effective management program for type 2 diabetes is exercise and dietary restrictions. That's it. Okay?
Do you get type 2 diabetes from eating a lot of complex carbs, or is it just mainly simple?
It's not only the complex or simple, it's also the amount. If you're going to be stuffing your face with potatoes and pasta and not burning the calories, you're going to get type 2, okay? But if you are a power lifter or a bodybuilder and you need to eat a lot of carbohydrates to provide the fuel for the muscle building, you will eat, like, you can have legitimately like 10,000 calorie diet a day, which is insane, and not develop type 2 diabetes if you burn it all, if you're a professional athlete, okay? I don't know if you're familiar with the guy who played Mountain in Game of Thrones. No? Okay. Are you familiar with Game of Thrones? Okay. There's a dude, Icelandic dude, who's like 6'7", I don't know, 300-400 pounds, 1,037 pounds deadlift. His diet is 15,000 calories a day. There was a study in Louisiana, they wanted people to eat 4,000 calories a day. They had to put nurse next to each participant to force feed them. A person cannot, and it was like obviously, if you go to Cheesecake Factory, 4,000 calories is like a dessert. But you try to eat normal, more or less, it's an insane amount of food, okay? Hypoglycemic blood glucose is low. So pancreatic cancers, especially if you have a pancreatic tumor which produces insulin, can lead to this. A very much prolonged endurance exercise can lead to hypoglycemia. Okay? You have to really like push it all. Muscle seizures, not seizures, contractures, tremors, you weak, yes. And you just need to eat something. Okay? Does that make sense? So now we're going to talk about the chemical properties of monosaccharides. And we're going to start with the fact that if you have an aldose, it can be oxidized. Okay? Does that make sense? So there's a statement here. Small amounts of the open chain form present. So monosaccharides can exist in the open chain form, which you can see on the slide on the left. Okay, or, as we will see, they can exist in the closed chain, in the form of a cycle. The open chain form, if it contains an aldehyde group, can be oxidized to become an acid. So, a glucose, for example, becomes gluconic acid. If a monosaccharide contains an aldehyde group, we call it a reducing sugar. Glucose is an example of a reducing sugar. It can be oxidized by a reagent such as Benedict solution. Remember the one that we just talked about? And I want to remind you all that Benedict solution specifically oxidizes the following arrangement. So you have to have a carbonyl group and the OH group next to each other. Does that make sense to you? Okay. So when you need to name the product of the oxidation of a sugar like a glucose, so glucose is oxidized to gluconic acid. You replace OSE with the onic acid. Does that make sense to you? Good? All right. Now, there is an interesting situation with the keto group. So if you think about the fructose sugar, it contains a keto group, which is arranged like this. Okay? So you can see that it's not terminal. Everybody agrees with that? Now, you may remember that ketones, this is the ketone, they cannot be oxidized further into some kind of an acid. Right? But if you place fructose, which is a keto hexose and contains ketone group, usually not oxidized. If you place it in the basic Benedict solution, the keto and hydroxyl groups get rearranged, okay? And essentially, this rearrangement converts fructose to glucose. Now, glucose, in this case, contains aldehyde group, okay? So essentially I have a rearrangement of a keto group to aldehyde. Aldehyde group can be oxidized to acid. Making sense so far? Cool. So this is what we just saw, what I just demonstrated to you. So I have a rearrangement of the keto group to the aldehyde. So you go from fructose, which is the ketose, to glucose, which is an aldose. Sounds good? Now, if you remember our previous conversations about aldehydes and ketones that we held not that long ago, we mentioned that these guys can also be reduced, right? You can reduce them in the corresponding alcohol, either primary or secondary. So, if you take an aldose, such as glucose, and you reduce it, you produce a primary alcohol, which we call alditol. Okay? Am I making sense? The term sorbitol, does it sound familiar now? Yes? If you use sugar-free chewing gum, sorbitol is what gives the sweet taste. It gives the sweet taste, but it doesn't have the glucose effects. You see what I'm saying? We'll get back to this. Okay? So the naming for the sugar alcohols comes when you replace O's with itol. Okay? So for instance, the sugar mannose, you replace OSE, you get mannitol. Okay, I'm going to highlight the replaced part. Okay, xylose, xylitol. Am I making sense right now? So this sugar, xylitol, sorbitol, mannitol, are often used in sugar-free products. And the reason for it, if you will add regular sugar or glucose into gum, it's not good for your teeth because bacteria in your mouth will use glucose, and if you use sugar, then fructose as well, to grow and reproduce, and essentially, as a collateral effect, you're going to have acid on the surface of your enamel that will break down your enamel, right? When you use the sugars instead, you get a sugar-free gum, which is much safer for your teeth. Okay? Sounds good? So, blood glucose testing. Okay, so, well, okay. Normally, when we eat sugar, or glucose, whatever, and the glucose ends up in the blood, it is filtered in the kidneys, but then kidneys completely reabsorb it. Okay? So like you have like 200 milligrams per 100 mils in a urine, and it all goes back. Nothing is in the urine. No glucose is in the urine. If you have too much glucose, your kidneys just don't have the capacity to reabsorb all of it, and some of it ends up in the urine. Okay? Does that make sense? Now, how do we detect it? Glucose can be oxidized, so there's a strip, and within that strip, there's a chemical indicator, the dye, methylaniline, and two enzymes. So glucose oxidase converts glucose to the gluconic acid. And the side product, hydrogen peroxide, oxidizes 2-methylaniline, resulting in the coloration of a strip. Okay? So you can see here, did we do that? No, we didn't? We're going to do it. With not with the real urine, with the fake urine, but we're going to check fake urine for the presence of glucose. Okay? Different color distribution, like, yeah, this is what it's supposed to look like. Urine should not have any glucose in it. So, I actually have a question, rather non-conventional question. So obviously diabetes, at least type 1 diabetes, did not appear yesterday, right? So how do you think physicians tested whether a patient has diabetes or not? No. You cannot do anything with the blood. So you are a physician in late 1800s, like 1895, and you have a patient, you have a suspicion that this patient has diabetes. The only option is the urine. What would you do? There are two options. Yeah, kind of. Not completely. Glucose, what is it? Sugar. So how would you test if urine has sugar?
Taste it.
Taste it. I'm going to taste it. Now, remember, and I'm not like, folks, midstream urine is sterile. The only reason why we consider it to be, ooh, yucky, is because of the organ it comes out of and the overall social stigma associated with reproductive organs. That's it. Midstream urine is absolutely sterile. It is just as clean as the tears. Okay? Does that make sense? What is another option? A little slower. Works only in the summer. Still urine. Put in a cup, put in a windowsill. Flies. Flies and wasps. If they get attracted to it, it's probably sweet. Not particularly reliable, but at least you don't have to try. Okay? That makes sense? Okay. Disaccharides. So there are three most important disaccharides that we're going to talk about. So first of them, you can see the lactose, but I'm going to skip through this and I'm going to get straight to the matter. So we have three disaccharides that you must know. What they consist of, how they're produced. If you take 2 molecules of glucose, okay, and combine them, you're going to have a disaccharide called maltose. Are you familiar with the term malted beverage? That's maltose. Beer is maltose. Okay? Anything malted, actually. Doesn't have to be beer, anything that contains malt. You combine glucose and galactose, you have a milk sugar, lactose. And if you combine glucose and fructose, you get a table sugar known as sucrose. Okay? So, maltose, I mentioned malt sugar, 2 glucose molecules. I don't think we mentioned alpha refers to the position of one of the hydroxyl groups in the glucose, and D refers to the optical isomer. You get it from starch hydrolysis. Okay, so cereals, candies, sure, but just natural process of fermentation. Think about malt fermentation, whether somebody tries to make a beer or whiskey. Okay, you have, for instance, you have barley, right? It's a malty grain. You ferment it. Carbohydrates from barley get broken down, and one of the products is maltose. Okay? That makes sense? So this is why we call it an alpha maltose. Let me explain. So first of all, the bonds between 2 monosaccharide called glycosidic. Does that make sense? Good? The term for any bond between 2 monosaccharides is a glycosidic bond. Second, what you see here, this, does not look like a line formula, okay, that we saw before. See, this formula looks very different from this formula. So in the solutions, closed form is common in the solutions. Does that make sense? Okay? So when you start looking at the maltose, first of all, you see that glycosidic bond is formed between carbon 1 of the one glucose and carbon 4 of another. Am I making sense? Can you see that? Everybody? Did you see what I just labeled? Okay? So this is why we call it 1,4 glycosidic bond. Am I clear? Good? Now, the hydroxyl group at carbon 1 can be either above or below the ring. Am I making sense? So in this example, it is below the ring. We call it alpha OH group. Is that clear? Can you see that?
The ring is just that.
This is the ring. And if you remember the wedge dash approach, so you see how these bonds are thick? It means that they're facing you. Like the position of that molecule is not in the plane of the screen. Its frontal part is kind of sticking out. We just can't really make it 3D. Okay, do follow. So this hydroxyl group that I pointed at is below the ring. If it's below, by definition, we call it alpha. So this is why this bond is alpha 1,4 glycosidic bond. Sounds good? Because, for instance, here, look at this, in this example. This OH group it is above the ring. Does that make sense? Above the ring means that it's beta. So the bond is beta 1,4, not alpha 1,4. Am I making sense right now? Okay. Lactose, which we just described, okay? So first of all, the components: beta-degalactose, alpha-glucose. The bond is between carbon 1 and carbon 4. So, since hydroxyl group at carbon 1 is in beta position above the ring, we have beta 1,4 glycosidic bond. Okay? Obviously, it is found in milk products. Right? And this is the bond. Making sense? You absolutely should know the type of a bond in each of these 3 disaccharides and what monosaccharides comprise them. So I can ask you, like, lactose, what is it made of? Galactose and glucose. What type of bond connects them? Beta 1,4 glycosidic. Okay? Sucrose. Now, when you look at this, the connection is established between the first and the second carbon, right? So we have 1,2 glycosidic bond. Am I making sense? Okay? Now, in this case, since this OH group here is in the beta position, while this group is in alpha position, we're talking about alpha beta 1,2 glycosidic bond. That name reflects that hydroxyl group at the carbon number 1 is in alpha position, while the hydroxyl group at the carbon number 2 in the fructose molecule is in beta position. Alpha and beta position. I misspoke. Okay? Now, an important feature about sucrose. Sucrose can form an open chain. Am I making sense? Which means it cannot have that free aldehyde group and cannot react with Benedict's reagent. So this is one way to distinguish sucrose from either lactose or maltose. Okay, so that's the sucrose formation. Okay, so alpha 1, beta 2, so you end up with alpha beta 1, 2 glycosidic bond. So sweeteners. We set the reference point kind of randomly. The reference point is sucrose, and the value is 100 for sucrose. Anything that is sweeter is a greater value. Anything that is less sweet is a lower value. So, just first of all, sucrose. Sugar is sweet. Everybody agrees? Milk is not, because lactose is much less sweet than the sucrose. Beer isn't sweet as well. It can be kind of deceptive because it is not sweet, but it gives a lot of glucose into the bloodstream, maltose. Am I making sense? When you look at monosaccharides, look at fructose. Fructose is much sweeter, so it can be used as a sweetener for people with diabetes. So it's a little bit safer way for them to use fructose instead of glucose or sucrose in the food. So xylitol, which is essentially a product of reduction of glucose, has the same sweetness as the sucrose, 100. Now, this is just insane. The sweetness of stevia, 150 times more than the sucrose. Does that make sense? And in addition, these non-carbohydrate sweeteners, they don't influence your blood glucose levels. There are other issues associated with them, but it's not a chemistry conversation. It's more of a physiology, microbiology conversation. All right?
What would you put any of that stuff in? What would you put any of that in?
Okay, just some examples. So, this is sucralose. If you will compare a sucralose here with sucrose, okay, I want you to take a long glance at sucrose here. See that? Good? Can you see sucrose? Take a look at sucralose. A lot of OH groups are replaced with chlorine atoms, which makes it 600 times more, 600 times sweeter than sucrose by itself. Now, aspartame is actually kind of cool because does it look anything like carbohydrate? No, it does not. It's completely different, right? That makes sense? So there is an amino acid, phenylalanine. Yes, that's methyl ester of phenylalanine, and that is aspartate. So basically, you have two amino acids, phenylalanine and aspartate, that are slightly chemically modified. So first of all, it is safe. Yes. these amino acids found in the human proteins, whatever. But what I find fascinating, why do we feel sweet taste? We have receptors on our tongue, on the cells on our tongue, that will bind sugar molecule, for example, right? That makes sense? And when they bind that, like this is the receptor, okay. So this is the receptor. This is sugar. When sugar binds to the receptor, you get a nervous signal. Make sense? Somehow aspartame can bind to the same receptor that the sugar binds and can stimulate it just like sugar does. It's kind of a decoy, okay? So same receptor, but now, for some reason, you have aspartame binding. And you feel sweetness. Making sense? Now, let's talk about what monosaccharides are going to be found in each one. So in lactose, what do you have? Galactose and glucose. In maltose, what do you have? Only one of them. And in sucrose, fructose and glucose. Yes. Okay, makes sense? Polysaccharides. I'm going to skip this slide because it's not particularly informative. We're going to talk about all that kind of stuff. So polysaccharides are usually polymers of the glucose. So 3 polysaccharides that we're going to pay particular attention to are amylose, amylopectin, and cellulose. So basically we have a bunch of glucose molecules joined together. So first amylose and amylopectin. So let's start with the amylose. You can see that amylose is unbranched. Amylose has a straight chain of glucose subunits. It is wrapped into a nice little helix, but other than that, it's a chain. Does that make sense? Good? Then we have amylopectin, which has a branched structure. Okay? Good? Now, amylose and amylopectin together form starch. Okay? Does that make sense? So amylose represents about 20% of starch. Obviously, please don't memorize the numbers. I want you to understand that amylose, like bullet points, amylose, straight chain, consists of individual alpha-D-glucose building blocks. And these building blocks are connected by alpha-1,4 glycosidic bonds. Did I make myself clear? Okay? Amylopectin, more, 80%. It's branch chain. Okay? And the continuous chains are formed by glucose residues connected by alpha-1,4, just like in amylose. But the branching comes from alpha-1,6. Let me go back to this fella. Do you see this particular bond right here? Okay? So 1,6 alpha-1,6 glycosidic bond. Is that clear? Good? Actually, you can prove to yourself that amylose and amylopectin, in other words, starch, consist of glucose. Can you digest starch? Yeah. So, the digestion of starch starts in your mouth, okay? Look at this. Starches are easily hydrolyzed in water. Can you give me an example of a starchy food? The simplest, like ready to eat. I mean, I would not nibble on like raw potato, like ready to eat. You go to the grocery store, huh? Bread. Get a piece of bread, put it in your mouth, chew it a little, but just let it sit there and let the saliva do its job. Saliva contains an enzyme called amylase, salivary amylase. It will start breaking down starch, releasing glucose. And if you hold it like for several minutes, which we usually don't do, you will start feeling the sweet taste of glucose in your mouth. That makes sense? Glycogen, similar to amylopectin. So glycogen, glucose polymer, liver and muscle of animals. It's an animal polymer. Okay? So glycogen stores glucose effectively, and when our blood glucose drops, glycogen is hydrolyzed in our cells. Okay? Does that make sense? Ever heard about the procedure called carb loading? No? Maybe? Yes? So, some athletes do that. What they do, they basically starve themselves for carbohydrates for a couple of weeks, exhausting all glycogen storage in liver and muscles. The night before the race, they had a massive bowl of pasta. And because of that starvation stimuli, your liver and muscles accumulate as much glycogen as they can. And then they go for a race and use that glycogen storage to provide energy for them to run. There are certain drawbacks in this we're not going to talk about, but that's an explanation. That's where we store glycogen in the liver and muscles. I want to highlight that the units are connected by 1,4-glycosidic bonds, and the branches are formed by 1,6 alpha-1,6 glycosidic bonds, exactly like in amylopectin. From the standpoint of bonds, glycogen and the amylopectin are essentially the same. Cellulose is different. Glucose units, okay, unbranched chains. Now look at the bond. It's not alpha-1,4, it's beta-1,4. Making sense? Now, that statement is not correct. Cellulose can form hydrogen bonds with water, but the molecules are too large to be dissolved. Now, listen closely. If you take a piece of paper and you drop a water on it, will paper absorb water? Yeah. That cellulose will interact with water molecules. It's not going to be dissolved, but it will interact. Am I making sense? What I think is more important is its function. So first of all, it forms cell walls in plants. So when you see like trees, for the most part they stand upright because of the cellulose in the cell walls. Okay? But there's another interesting feature. We, humans, cannot break down beta-1,4-glycosidic bonds. So, this is beta-1,4-glycosidic bond. Sorry, I'm going to go all the way up. This is alpha-1,4-glycosidic bond. They are very different. Does that make sense? So, we can't break down cellulose. Technically speaking, if you decide to eat a piece of paper, you eat fiber. This piece of paper, I mean, you chew it, it will like get into mush, and it will come out just cellulose. You're not going to get any energy from it. Am I making sense? The food like celery, it's pretty much cellulose and water. It, to a large extent, acts as just an absorbent that goes through your digestive system. Ruminant animals, on the other hand, such as cows or horses, they can digest cellulose. Couple of tricks. One, it's not them, it's bacteria and archaea inside of their stomachs. Two, their stomachs are ridiculously complicated. The food goes from one stomach chamber to another, back and forth, and it takes hours to break down cellulose. It is not easy. Does that make sense? Good? And as far as I remember, cows even regurgitate the content because it has to be churned out. Okay? I mean, you can find cellulose everywhere, from wood to cotton here to all the plants that you can think of. Okay? So, polysaccharides, let's identify them. What do you have on the left in the cotton? What kind of polysaccharide are you going to find in the cotton? Cellulose. And the type of the glycosidic bond? Beta 1,4. Potato. It is what? What polysaccharide are you going to find in potato? Starch, which is comprised of amylose, remember linear, alpha 1,4, and amylopectin, in which alpha 1,4 bond produces the linear part, and alpha 1,6 is responsible for branching. Does that make sense? So we are doing phenomenal. We are going ahead. So it's a great job.